Okay, so if you can remember, up to the previous week, we have discussed about what is inside the computer in details about registers, how the RAM works, right? The concept of, I think, memory address register and memory buffer register, the synchronization, and then how the programming languages has evolved. In fact, I'll in fact mix these two concepts because firstly, remember one thing, that when you will write a program, though that is not required in today's programming languages like Python or Java, but truth to be told, when you program in some programming languages like C or Rust, uh, it is good. It is better that you know what is happening, that what is happening with that program inside, right? And once you know this, truth to be told, you will not face any difficulty in learning any programming language. Okay, so I will discuss inside the computer again at a bit deeper level now. And this is the last discussion of the computer architecture in this course. If you want to know in much more details, those who are in computer science or IT will go through the computer architecture course. So if you can remember, till now we have seen that there is the CPU, and in the CPU till now we have partitioned it into three parts. One is the registers, where the registers are there. One is the ALU, the arithmetic logical unit, and the other one is the control unit. And here is the RAM, where the instructions are already in the RAM. Suppose the instruction is somewhere here, right? And as you know that each instruction resides at a particular address, starting from the lower one to the higher one. These are all we have discussed till now. And another thing is that uh, any compiled programming language like C or Rust, in fact, as we are going to study about the C, Python is not compiled. Okay, Java is first compiled, then interpreted. Python is purely interpreted. But I'll not going into the discussion of what is interpreted. Uh, just one thing, that the interpreted languages do not get converted into assembly language. Okay, whereas in originality, within the machine, it is at the end with the assembly instructions that will run. So how the interpreted languages execute, that's a bit deeper concept, where in fact they do not get converted into assembly language, rather they invoke some internal functions, which in fact execute in the name of those programs you write. But I'm not going into that details because that is too much deep concept at this level. So any compiled programming, any compiled programming language is the simplest case, gets compiled to assembly language. Whether it gets compiled directly to assembly language like the C or Rust, or whether it invokes some internal function that executes on the machine. That means that the like what happens in the interpreted programming language. At the end, it is instructions that execute. these instructions that get executed on a processor. Okay, and these instructions, as I've told you, the instructions are in fact generally in the terms of 1 0 1. That means in the sequence of ones and zeros, but we can make it one-to-one convertible with assembly instructions. So if I write something like add, say, RAX, RBX, RCX, you can be rest assured that there is some ones and zeros sequence which is in the machine instruction format, and it's converted by the assembler, right? So we can use them interchangeably. So that's why it is called assembly instructions. So rather than assembly language, it is also sometimes called assembly instructions. Some of you is unmuted. If you have nothing to ask, you can mute yourself. So it's assembly instructions and it's machine instructions. Eventually, at the end, it is the step-by-step instructions that get executed into the processor for that particular application. So maybe there is some instruction here, maybe say 1 0 1 1 and so on. There is other instructions here, maybe 0 0 1. And now what happens is that firstly, when I'll discuss about the ways from the next class. In fact, tomorrow and on the Saturday, I'll finish up the concept of operating system. In brief, so when OS loads the application from hard disk to RAM to some specific address of RAM, address in RAM, it also loads, though several other things happen in between, but I'm not going into the details. It also loads, if you can remember, the instruction pointer register. What does instruction pointer register contains? I discussed it previous day. Can any of you tell me? Anyone? What instruction pointer register contains? The address of the next instruction to execute. Okay. Instruction pointer holds the address of the next instruction to execute. Right? So it also loads the IP register with the address of the first instruction. So there is some instruction pointer register. Okay. That contains the next next instruction to execute, and the address of this first instruction, that means this instruction, address of this instruction is loaded in the instruction pointer. Now CPU fetches the instruction. From RAM. If you can remember, it fetches in multiple steps. It sends the address, which is in fact IP register, instruction pointer register. It sends the address of our address bus. That we have discussed previous day as well, I think. In the previous day, I've discussed about the 3 buses, right? Address bus, data bus, and control bus, right? And there I have also shown that eventually how going via these buses, that address goes via address bus, but for the synchronization, it first gets into the memory address register. Memory address register waits till all the bits of the address comes in. Then in the next clock cycle, it gives the address to the RAM. RAM looks into the address, and then it loads whatever data is at that particular address over the data bus. And again, for the synchronization purpose, the content of the data bus goes to the memory buffer register, MBR, which on the next clock cycle goes to the CPU, right? That was what I've seen for the synchronization purpose. What the system does. So it sends the address over address bus. The address comes to MAR, which is memory address register. Then the address is fed to RAM from the memory address register. Okay, the address goes to RAM. RAM sends the information, whether it is data or whether it is instruction. RAM does not know that. It only looks into the address, and it blinds you, and it blindly sends whatever is present at that particular address. It does nothing more than that. So RAM sends the information at the address, that comes to MBR, memory buffer register, and then the information. Again, this, remember, these two things, the address is fed to the RAM and the information going to the information goes to CPU. These two things happens at the clock cycle synchronously. In fact, these MAR and MBR are there for the synchronization purpose, if you can remember from our previous day's discussion. Now, instruction has been fetched. The next step, control unit, that means CU, decodes the instruction. Again, if you can remember from our previous day's discussion, by decoding means it takes the input signals over the wires, ones and zeros and so on, and there is a particular synchronization circuit sitting in the control unit, which is again designed using the particular algorithms, and it sends the corresponding signals. Maybe if there is an arithmetic operation, then a signal will go to ALU. If there's some movement operation, the signal will go to the registers and memory and so on, right? So the CU decodes the instruction and sends appropriate signals. Now I'll just use certain special instruction to show what in fact is happening. If the instruction is something like, say, add RAX, RBX. Now These are special cases. Add RAX, RBX, RCX. That means add the content of RAX and RBX and put that into RCX. Suppose, for example, where RAX, RBX, RCX, again, if you can remember from our previous day's discussion, they are the name of 3 registers. There are 16 general purpose 64-bit registers, right? Among them, the 3 are RAX, RBX, RCX, which we can access programmatically. Okay. Now, what it will do? In that case, the signal will go to RAX and RBX registers. Okay. Data from RAX and RBX will be fed to ALU. Okay, let me just picturize this. There is an RAX register here, and there is an RBX register here. And suppose this is the ALU sitting here. Generally, ALU is drawn using this symbol. Now, RAX is fed to the ALU, RBX is fed to the another side of the ALU. Okay. Now here, the control unit has already sent the signals to these 2 registers that send data. Okay. Now, control unit also sends a signal to adder. Okay. That means addition will be done and not the multiplication circuit, division circuit, they will not come into action. Okay. So, in the adder part, then the addition of RAX and RBX is done, then it is stored in the RCX register. Okay. And CU also sends a signal to RCX to store the data from the output line of adder. That's it. This is what is happening. So control unit sends the signal to RAX and RBX, adds them, stores the data to the RCX. Is the concept clear till now?
Yes, sir.
Any of okay. But remember one thing, that variables, all the variable that you will declare, variables stay in RAM, in memory, not in the registers. They need to be brought to registers. They need to be brought to register before any operation. Okay, and one possible instruction is for that is move instruction. Maybe say this simply means maybe that there is some data in the RAM at the address ABCD, that's need to be moved to the RAX register. Okay, that means, this simply means bring the data at address 0xabcd. This is a memory address, right? And my program is telling that there is a data at address 0xabcd, right? I've taken a hypothetical address and I have written it in hexadecimal just for an example, considering a 16-bit machine. There is a data at address 0xabcd. Bring that data and put it into the register RAX. Okay, so bring the data at address 0xabcd to RAX register. Right, and what happens here after decoding? See, here up to this, the control unit has decoded the instruction. For the addition instruction, it just sends the signal to the registers and to the adder, nothing more than that. Okay, for such move instruction, what it will do, it will load the address bus, because see, the control unit has understood that you want to fetch the data from memory again, so it has to access, it has again to go to memory, bring the data and put that in RAX. So it will load the address 0xabcd over address bus. That will again come to the memory address register. I am not writing the details, but you can fill that up. Does not matter whatever address it is, that will always be synchronized via memory address register, and does not matter from whatever data it is going from memory to CPU, it will always be synchronized via memory buffer register. Okay. So to save the time, I am not filling up the details in between. RAM sends the data. In fact, RAM does not know whether it is data or instruction. Again, RAM simply has seen the address 0xabcd. It will put on the data bus whatever data is at, whatever information is at that address, nothing more than that. Okay, it is only CPU that knows that I am bringing information or data. Clear? So RAM sends the data over data bus, but this time it does not come to the control unit, because control unit has already decoded that. This data comes to RAX register. Control unit has already sent a signal to the RAX that accept the data that is coming to you. That means there is an incoming data on you, and RAX accepts that in the next clock cycle. Is it clear? Is the concept clear till now?
Yes, sir.
Okay. And there is just its reverse. That means move, say, RCX to, say, 0x1234. That means put the data of address, sorry, put the data of RCX register at memory address one, two, three, four. So this is now the direction of the data is just reverse to what you have seen here. Here the data is going from memory to register. Here the data is coming from register to memory. Register to memory this time. So this simply looks like now this. There is suppose this RCX register. This information will now come to in this direction. Maybe this is the address of this memory location is 1, 2, 3, 4. The data will now come in this direction. So in fact, one thing that I'll discuss after this, the procedure is, I think, now clear to you. It will load the address 0x1234 of our address bus and the data of RCX of our data bus. Now something is different here because data is not coming from memory to register. It is coming from CPU towards the memory. Okay, so it will load both address bus and the data bus together. Address as usual will come to MAR and data will come to MBR. Okay. At next clock cycle, the data will be returned to the address. Okay. So I think one catch from here, whether I've noticed it or not, address bus is unidirectional. Is unidirectional. It goes only from CPU to RAM. Data bus is bidirectional. Because data can go from CPU to RAM as well as it can come from RAM to CPU. Okay, data bus is bidirectional, but address bus is unidirectional. Control bus is unidirectional. Okay, but it varies. The fact of control bus is varies because in some devices the interrupts come to the control unit. So in that scenarios, control bus is bidirectional as well, but I'm not going into that level of details. So in general, control bus can be considered as unidirectional because the signal only goes from control unit to all other devices around. Okay. Any query till now? Now, though there is another type of instruction, that is jump instruction, but I'm not going into that level of details. Now, these arithmetic instruction and two move instructions in two different directions it is sufficient for simple programs, arithmetic operations. Like suppose you are writing something, say C equals A plus B. Okay, in C program, suppose you have written something like C is equal to A plus B, and let the address of A, B, and C be, suppose 0x 1230. This is where A is, 0x1234, that is where B is, and 0x1238, that is where C is. Okay, its equivalent assembly instruction, again this is just hypothetical because it can vary from machine to machine, and language to language, that means assembly language to assembly language, but concept will be same. Move 0x1230 to some register RAX. What it does, it is bringing the value, the variable A to RAX registers, right? So bring value, I'm considering this as comment, value A to RAX register. In fact, this is not comment, is used in GNU assembly. Is hash. Just 1 second. Bring value A to RAX register. Okay. Then move 0x1234 to RBX. Add RAX RBX and put that in RCX. Then move RCX to 0x1238. So bring value B to RBX register. Add the two values and place in RCX and take RCX to variable C. So eventually C is containing the sum of A and B, though in reality all these variables are declared in with relative to some another register that is called stack pointer. Again, this is just for simplification I have written. In original assembly instruction that will be converted, you will see that in terms of something RSP, but I am not going into that level of details. This is a simplified version of what will happen inside the system. It will first, so if you want to add C is equal to A plus B, the information of A will go to at say RAX register, the information of B will go to say RBX register, they will be added and the addition will be placed in the R6 register, and then the R6 register will be brought back to the variable C. And there are steps that I have discussed in previously. And remember, whenever, just remember one thing, whenever an instruction has been done with IP, that means the instruction pointer register, IP register will be added to point to next instruction. So suppose the IP register, this is your overall program. Suppose IP register has first, the operating system has load the IP register with this address first. The CPU will execute everything about this address, right? After decoding, it will bring the data. That is called fetching the data. In fact, in architecture term, fetching the data and put that into the register. Now, once this instruction has been done, the IP will be implemented. Okay. As for example, just as an example, in today's 64-bit machine, 64-bit means instructions are how many bytes?
8 bytes.
Correct. The instructions will be of 8 bytes. So just 1 second. Let me draw it just roughly. So if the first instruction is here, say 0x1230, okay, instructions are of 8 bytes. Next instruction will be at 0x1238, right? Because there are 8 bytes in between. There are 8 bytes in between two instructions. So IP will be added, more specifically 8 will be added with the content of IP. 8 will be added with content of IP. After every instruction. And this addition will also be done in the ALU. Okay, so it now points to the next instruction. The next instruction will be executed in the similar manner. In exactly the similar manner, for starting from the first, that will be fetched, control unit will decode, the data will be fetched into the RBX, done. Then IP will be added with 8 again. So it is now pointing to this instruction. Now nothing will be fetched. The signal will go to RA. First, the instruction will be fetched, obviously. Control unit will decode, CU will decode, and then it will send the signals to RAX, RBX, and adder. They will add and put the data in RCX. Done. Then IP will be added with 8 again. So this instruction will be executed, and now the address and data both will be loaded, and the RCX data will be loaded into the value of C at the address of C variable. And we'll see the C variable containing the values of A plus B.
सर
हाँ बोलो.
सर ये इंस्ट्रक्शंस कौन देता है कि आप इस एड्रेस का कंटेंट RAX में मूव कीजिए या फिर ऐड करो वगैरह?
Okay. When you will write this program, the compiler will convert this into the assembly language. Assembly instructions. Okay, then the assembler will convert these instructions into the corresponding binary, right? So maybe after let me write this as a star here below. Then assembler will put will convert into machine language that I have discussed previously.
Yes, sir.
Now these machine instruction that we'll see, that is this 1 0 1 1, say there are 4 instructions, so so there will be how many, so there will be total 32 bytes because each instruction is of 8 bytes, right? So there will be 32 bytes. Okay,
Okay.
now this is your application, this is on your hard disk. Now your OS will load it into, say, this memory address. Okay, sorry, say this memory address, and OS itself will tell the CPU that its first instruction is at, say, 1230. That will be already in the instruction pointer register, and then from that point onward the CPU will start executing this program instruction by instruction.
So you mean, sir, instruction is given by OS?
Instruction, obviously, yes.
Okay. Okay.
Instructions are brought by the OS, right?
Okay.
See, OS itself does not do nothing. That I'll discuss in the next OS discussion. I'll start the discussion of OS now. That I'll finish within this week. OS itself does nothing. OS only brings the instructions from the hard disk to the RAM. Okay, and tells the CPU that here I have brought my application. This is its first instruction. Starts executing it. Right? CPU simply follows that. Clear? Otherwise, this instruction has been generated by the program written by you. That means the program that you have written, uh, instructions has been generated according to that program by the compiler. Right? Any other query?
No.
Uh, Anyone else regarding all this discussion? Because from the next point, I am going to the another topic, the topic of operating system. The discussion of architecture will be up to this. Till I'll say I have discussed pretty much advanced topic, but don't worry. Many of them, this is just for the interest, nothing more than that. So, any query regarding the architecture part? Okay. So let me discuss about operating system.
Sir, no doubt, but please share the content
Yeah,
soon.
sure, sure. I'll
Sir,
हाँ बोलो.
sir, notes. Sir, please
हाँ,
share the P.
ओके. इस हफ्ते का क्लास हो जाए, मतलब कल 2 घंटे का क्लास हो जाए, उसके बाद इस वीकेंड में मैं पूरा शेयर कर दूंगा. ठीक है? या फिर देखते हैं, आज अगर टाइम मिलेगा तो आज ही शेयर कर दूंगा, बिकॉज इसके बाद इस हफ्ते और भी 4 घंटे का क्लास होगा. कल 2 घंटा और फिर 17 सैटरडे को 2 घंटा. ओके, सो OS is a software, right? Okay, OS is a software that lies closest to the hardware. In fact, OS manages the hardware. This is very important. OS manages the hardware and creates a complete environment for the application to run. Okay. See, OS, like the other softwares you see, like the Microsoft Office or maybe the VLC Media Player, they do something. You see that they are doing directly something. VLC Media Player is playing the corresponding song or movie, or maybe on the Microsoft Office you are writing the document. You are directly using that. It seems that they are doing directly something for you. But this VLC Media Player or the Microsoft Office, they are in fact are dependent on the underlying operating system on which they are running. Operating system itself is not doing anything. If you consider equivalent to the application software that you are using, operating system itself is not doing anything, but it is creating the complete environment such that the applications you are using, they can do something for you, right? So it is quite something like this. See, the diagram is drawn something like this. This is the hardware, the core. Consider this the core of the earth. If the complete computer system is the earth in itself, this is the operating system. This is the OS. That is, you can consider that our soil, right? So that upon which on this soil we can move, we can create a complete sustainable lifestyle. This is the application software on which everything executes. So OS itself does nothing. It only controls the hardware. It is only the communicator between the application software and the underlying hardware. Every communication between the application software and underlying hardware must happen through operating system. And OS does this task by performing several independent functionalities. Firstly, the functionality of OS, if we can focus on it, firstly, process management. Then memory management, then the files and IO management, and computer security. Okay, we can overall divide the task of the operating system into these four groups. Though in several studies that files management, IO management um, are kept in separate parts, but this is eventually the the four functionalities of the operating system. Okay. Uh, Today I will not start the new topic because after discussing only for 5 minutes I will stop anyway. So from tomorrow we will start process management study.
So what is I/O?
I/O is input output devices. That means your monitor. Let me just
What?
discuss this in brief. I/O device, that means the input output device via which you provide the input to the machine and you see the you receive the output from the machine. See, CPU, RAM, they are the core. CPU, RAM, and your motherboard, they are the core. They are the heart of the machine. The rest is the are the extended versions of your machine. Like say we take input, we provide input via keyboard, right? So keyboard is an input device.
Yes, keyboard, mouse.
Yes, keyboard, mouse, joystick, they are all input devices. I'll tell you how operating system manages these IO devices. Whenever I am
Scanner.
pressing some key on the keyboard, bolo.
Scanner is also input device.
Which one?
Scanner.
Scanner. Yes, scanner is also an input device. Scanner is an input device. But printer is an output device. Though they are on the same device, but scanner will be the input device, printer will be the output device. Printer, monitor,
Speaker.
yes, speaker, they are output devices. Hard disk and network, they are both input and output, because you can read data from hard disk and write data to hard disk as well. Over the network as well, you can send data over the network, you can receive data over the network, right? So that's why they are both input and output. Though network is a concept, in fact there is a network card, if you can know, it is also known by Ethernet card, right? And as well as in laptops, this is the corresponding wireless card. They are both input and output device. Okay. Though today's motherboards, desktop motherboards also coming with wireless cards as well, wireless devices as well. So wireless, any network device and hard disk, they are both input and output device. Right. I'll show how operating system communicates with these devices as well. Not all of them. I'll just give you an overview. Obviously, it will not be a complete. There is those who are in computer science and IT, you will go through a complete course on operating system as well. Right. In
Sir,
one. Ha, bolo.
this network card means that NIC card, sir. Network
Yes.
interface card.
Yes. Yes. NIC card. That is also known goes by the Ethernet card. Okay.
Okay, sir.
So they are both input and output device. Now, suppose I'm writing something, say I'm pressing W or anything on the keyboard, a, a electric signal is going, that is generating, there is something called interrupt, but I'm not going to the details now. There are 4 classes to discuss everything about this. CPU, whenever the CPU will face the interrupt, an interrupt will go. Interrupt is a special signal. The CPU has a special lines to receive those interrupts, and it is always waiting there if some interrupt is coming or not. Whenever CPU faces some interrupt, it stops everything what it is doing, tells the OS that I have faced an interrupt, do something. OS looks into what interrupt it has faced, does the appropriate job. As for example, I am not showing this, but if I press Alt F4 here, this will close, right? So whenever I'll press Alt F4, CPU, that a particular key code combination, the combination of both Alt key code and F4 key code will go into the CPU. CPU will tell the OS that this key code has appeared to me, this interrupt has appeared to me from the keyboard. Keyboard has sent me this interrupt, and the key code is Alt and F4. What is to be done? OS will tell, everything is written in the OS. This is called interrupt management. Okay. OS will look into that what is to be done, and it will simply close the application, close the currently running application. That's why whenever you press Alt F4, whatever application you have there, that will get closed, because that is being managed at the operating system level. Operating system does not send it to currently running application. Whenever it says Alt F4, operating system immediately closes the currently running application. So, and if you do something as, say, if I press the mouse button, right, you see that this has risen up. In fact, again, whenever I press, rather than mouse button, the Windows button again, whenever the Windows button will go there, CPU will take the key code, tell the operating system that I have faced this interrupt with this Windows button key code, do something. OS will see and will do, and will simply tell the GUI that show this menu. That's it. Okay, I'll discuss about everything, how OS, CPU, OS more generally. CPU only tells the OS that I have faced this, do something. OS does the main job. And how OS does this, how OS manages these input output devices, I'll discuss in the upcoming classes. Okay, and obviously that was only about IO management. I'll also discuss about process, memory, and how files are arranged. And in this example, I'll consider only the Linux operating system and no other operating system. Okay, that is the flagship of operating systems, the Linux. So how the files are arranged on, files and directories are arranged in Linux system. I'll not discuss about the computer security because that is a pretty advanced topic. So I'll discuss only these core functionalities, these 3 core functionalities. Any query? Any query?
No, sir.
Okay. So I'll keep my discussion up to this. We'll see you tomorrow from 2 to 3. I'm stopping the sharing and I'm stopping the recording.